three-phase induction motor. Here we discuss equivalent circuit of three-phase induction motor, which is steady-state equivalent circuit, and performance characteristics for the three-phase induction motor. Here you can see three-phase induction motor basic parts: stator, rotor, and air gap between stator and rotor. You see here three-phase windings of stator, and these are the rotor windings, air gap between rotor and stator. This is three-phase power supply we give for stator. Omega s synchronous speed at which magnetic field will rotate. Omega m is the motor speed, nothing but rotor, at which rotor will rotates. Rotor speed is always less than the synchronous speed for the case of induction motor. That's why it is known as asynchronous machine. And three-phase induction motors commonly used in adjustable speed drives. Now, synchronous speed, right? Field will rotate at synchronous speed, right? Which is given by 2 omega by p. Omega s is the synchronous speed in radian per second, where ns is also synchronous speed in revolutions per minute, rpm. Here p is the number of poles, f is the supply frequency in hertz, where here omega is the supply frequency again in radian per second. So synchronous speed is given by 120 f by p, rpm. Synchronous speed 2 omega by p, radian per second. Motor speed. So motor speed is always less than the synchronous speed. So some slip will be there. So slip will be calculated by omega s, synchronous speed minus rotor speed by synchronous speed. So that rotor speed is given by omega s multiplied by the 1 minus s. Slip also can be defined as ns minus nr by ns. This is ns is in rpm, omega s is in radian per second. Now we will see steady state equivalent circuit, stationary equivalent, nothing but steady state equivalent circuit model per phase for the induction motor. We can see here stator part indicates xs rs, whereas air gap nothing but magnetizing part, it is shunt branch. We can show as shunt branch, which shows the magnetizing part, air gap, and this is the rotor part, okay, where rs is the resistance per phase of stator winding, rr is the resistance per phase of rotor winding, xs is the leakage reactance per phase of the stator winding, xr here, xr is the leakage reactance per phase of the rotor winding, where xm is the magnetizing reactance, where rm is the core loss component for the magnetizing shunt branch. See, stator current is divided into parts: magnetizing component and rotor current. Now, stator copper losses given by 3 times the is square rs, and rotor copper losses given by 3 times the ir dash square rr dash. Core losses in shunt branch, core losses will be there 3 times the Vm square by Rm, approximately equal to 3 times the Vs square by Rm. Yeah, here we can see the power flow in three-phase induction motor. P in input power, which is given by 3 V phase, I phase, cos phi. So air gap power, we can calculate air gap power by subtracting stator core losses and stator copper losses from the input power supply. And mechanical power developed is calculated from air gap power. So by subtracting rotor core losses and rotor copper losses from air gap power, you can get mechanical power developed. And power available at the shaft, power output, is calculated by subtracting friction and windage loss from mechanical power developed. So power developed in air gap, nothing but power from stator to rotor through air gap. Air gap power, we can say simply this is the rotor input power, which can be calculated by 3 times the IR square RR dash by S, and power developed by the motor, which is calculated air gap power minus rotor copper losses, which is given by air gap power into 1 minus S. Now torque, power developed equal to torque developed into omega m, right, rotor speed. So finally torque developed is given by power developed by the motor, nothing but mechanical power divided by rotor speed, also can defined as PD 60 by 2 pi Nm, here in RPM, here speed is in radian per second. So torque developed also we can define as air gap power by synchronous speed, mechanical power by rotor speed. Input power 3 Vi cos phi is nothing but Pc plus PSCU plus Pg. Stator copper losses, stator core losses, air gap power. Output power of the motor is power developed minus no load power. No load power means which is supplied under no load condition. Motor will just supply friction and windage losses, no? That is efficiency, output power by input power. If air gap power is very greater than PC plus PSCU and PD, power developed, is very greater than P no load, efficiency is simply calculated like this with this formula 1 minus S. If you know the slip, you can simply calculate it, efficiency with 1 minus S, this expression. Now generally value of magnetizing reactance Xm is very greater than Rm, which is core loss, which gives core losses. So Xm is very greater than Rm, and also Xm square is very greater than stator components, Rs square plus Xs square. So this shunt branch will come, we can bring this one here forward by neglecting this one. So Rm is very low compared to Xm, so we can neglect this one. So only Xm will appear here. From here to we can bring front here to make calculations simplification. So Vs supply voltage, Xm magnetizing component. So this is stator components, these are rotor components. Now stator current, nothing but input current, is divided into two components again, magnetizing component, this is rotor current. So from this we can easily calculate rotor currents. See, these two are in parallel now. Rotor current IR dash is given by supply voltage divided by Rs plus Rr dash by S plus J into Xs plus Xr dash, right? So from this torque developed Pg, air gap power by omega S, that is given by 3 IR square Rr dash by S omega S. You can substitute rotor current here. Finally, we get torque developed equal to 3 times Rr dash Vs squares S omega S Rs plus Rr dash by S whole square plus Xs plus Xr dash whole square. This is the slip. Omega S is synchronous speed, rotor resistance, supply voltage. Now we can see typical speed torque characteristics of the induction motor, 3-phase induction motor. You see here, if the slip is 1, nothing but slip, and 1 means rotor speed is 0. Slip 1 means rotor speed is 0. Slip 1, it is starting torque. Rotor speed 0 means it is starting torque. Slip S equal to 1, substitute here. If you calculate with supply voltage, that will gives the starting torque. So as the rotor speed increases, nothing but rotor speed increases, slip decreases from 1. As the rotor speed increases, torque developed also increases. At this point, torque becomes maximum, right? Where the slip at which maximum torque will occur is known as S maximum. Okay? Slip at which maximum torque will occur is known as S maximum. From this again, as the rotor speed increases, nothing but slip decreasing, torque developed also decreases. Finally, once slip becomes 0, if rotor speed becomes synchronous speed, it is not possible for induction motor. If suppose what happens, if rotor catches the synchronous speed, no difference between no relative speed between rotating magnetic field and rotor, so that no flux will be cutting, so that no induced EMF in rotor, so no currents, no torque. See here, at this point, if slip is 0, if rotor rotating at synchronous speed, torque becomes 0. Why? Because no relative speed between rotor and rotating magnetic field. So no flux cutting, no induced currents, no torque, right? So this is low torque, typical low torque characteristic. So this is the operating point where low torque and speed torque characteristics of the induction motor meets. That point is known as operating point. So at this speed, our induction motor will rotate. Now, why speed control? Maximum torque, nothing but pull out control, right? So this is the operating point where low torque and speed torque characteristics meets, okay, in steady state operation. If suppose, if you want to reduce the speed, that means operating point this one, what we do? Okay, for this we need to go for speed control. That means requires adjusting the speed of the induction motor.